The heart is a beating muscle that pumps oxygen and nutrient-rich blood throughout the body. Each beat is stimulated by electrical signals that pass through the heart muscle or myocardium. In order to examine the function of the heart, a doctor may perform a test called an electrocardiogram or ECG, also referred to as an EKG. During this test, electrodes are placed on the chest and recordings are then made of the heart's electrical signals. Sometimes the electrodes are also placed on the arms and legs. The electrical signals follow a set pathway through the heart, beginning at a spot called the SA node, which is located in the top right chamber or atrium. The signal then branches out through both the right and left atria, which contract and push blood into the lower chambers or ventricles. The electrical signal also passes into the ventricles via the AV node, and then travels down the tissue that separates these two lower chambers. Finally, the signal travels back up the ventricles, which contract and pump blood to the lungs and body. Variations from the normal electrical pattern may indicate damage to the heart due to a heart attack or heart disease. Often a patient will be required to perform a stress test during an ECG. A stress test usually involves walking or running on a treadmill at progressively increasing intensities while recording an ECG. This test allows the doctor to examine the heart's electrical activity during the stress of exercise.
The heart's conduction system controls the generation and propagation of electrical signals, or action potentials, that cause the heart's muscles to contract and the heart to pump blood. This electrical activity can be measured at electrodes placed at specific points on the skin, from which a composite recording is produced in the form of a graph. This recording is known as an electrocardiogram, or ECG, sometimes referred to as an EKG. A tracing of the overall electrical activity of the heart, resulting from the propagation of many action potentials. Let's look at what happens during a single beat of the heart, and how these events are depicted on an ECG. In a normal heart, each beat begins in the right atrium with an action potential signal from the sinoatrial or SA node, the heart's natural pacemaker. The signal spreads across both atria, causing the muscle cells to depolarize and contract, inducing a phase known as atrial systole. On the ECG, this atrial depolarization is represented by the P wave. The period of conduction that follows atrial systole and precedes the contraction of the ventricles is depicted on the ECG by the PR segment, a flat line following the P wave. When the signal leaves the atria, it enters the ventricles via the atrioventricular or AV node, located in the interatrial septum. It enters the bundle of His and spreads through the bundle branches and the large diameter Purkinje fibers along the ventricle walls. As the signal spreads through the ventricles, the contractile fibers depolarize and contract very rapidly, inducing ventricular systole. The ECG's QRS complex represents this rapid ventricular depolarization. Atrial repolarization also occurs at this time, but any atrial activity is hidden on the ECG by the QRS complex. Finally, as the signal passes out of the ventricles, the ventricular walls start to relax and recover, a state described as ventricular diastole. The dome-shaped T wave on the ECG marks this ventricular repolarization. On the ECG, the ST segment depicts the period when the ventricles are depolarized. The QT interval represents the time it takes for both depolarization and repolarization of the ventricles to occur. The sequence of events just described and the associated ECG trace repeats with every heartbeat. Remember, an ECG is not a tracing of a single action potential, but an amalgamation of the many action potentials that constitute the electrical activity of the heart.
To understand cardiac conduction, let's take a look at a slice through cardiac anatomy. The sinoatrial node where electricity begins is up in the right atrium. Now, to examine electricity, take a voltmeter, put it on your skin, and measure voltage over time. This generates the classical electrocardiogram, which starts with SA node depolarization, which causes the atria to contract, and that generates the P wave. The AV node gets depolarized, but it holds on to the electricity briefly for the PR interval. The left and right bundle branches carry the electricity down through the septum and around the left and right ventricles. This generates the QRS complex. This terminates in the J point, then there's a pause, then the ventricles repolarize, and that generates the T wave. This entire contractile phase takes 480 milliseconds or half a second, and then when you add relaxation, beat to beat is 1 second long.